So today, I'm very happy to have the opportunity to present our work called Implicit Chain of Thought, Internalizing Reasoning in Language Models. So this work was done with my postdoc advisor, Professor Yijin Choi, and also my PhD co-advisor, Professor Stuart Schieber. Before we talk about reasoning in language models, I want to start from reasoning in the human brain. So I think a lot of you might have seen this distinction between System 1 reasoning and System 2 reasoning many, many times. But here, just kind of a quick recap of System 1 and System 2 reasoning systems in the human brain. So when we reason about things, we have the System 1 reasoning system, which is fast, intuitive, and doesn't require efforts. So we can easily think of many examples of System 1 reasoning. For example, if I ask you a simple math question, like what is 2 plus 2, you probably wouldn't need to kind of like really think about it to know what's the answer to that. And similarly, if I ask you to complete a common phrase such as bread and butter, again, you do need to kind of like spend a lot of efforts to think about like how to do this. But on the contrary, we also have a different system of reasoning, called System 2 reasoning, which is slow and deliberate and requires a lot of efforts when we do such reasoning. So examples include like even if we just simply kind of make our math question a little bit more challenging to be, let's say, a 2-digit multiplication problem, I say most humans probably will need to think really hard to answer a question like, what is the product of 23 and 47? And similarly, there are a lot of like word puzzles or logic puzzles, different puzzles that require us to kind of invest in a lot of efforts to figure out the solution. So we have this System 1 reasoning and System 2 reasoning systems in our brain, but actually the boundary between System 1 reasoning and System 2 reasoning is not always clear-cut. So through repeated practice, we can sometimes internalize System 2 reasoning into System 1 reasoning. One good example of this is when we learn to play, say, a music instrument. So for example, imagine if a person learns how to play piano, that person might start from trying to kind of memorize what is the mapping from each music note to how to move their kind of muscles on their finger to press the correct key on the keyboard. But through repeated practice, this person might be able to kind of like just never think about this anymore, and instead only focus on kind of looking at kind of some music sheet and focus on the expression and the flow of the music. I think given our shared background, I think probably an even better example is when we learn how to type. I remember when I was a kid, when I first started using computers, I had to basically look at the keyboard and try to look for the key that I want to press, and then I kind of use one finger to press that key. But obviously today, when I code, like I do not need to think about which key I tap. It's almost like kind of a second nature of myself that I just think about what I want to tap, and then like my finger just kind of do it for me, and I do not need to kind of think about it. And I think through this example, we have already seen the benefits of this internalization process. So first of all, it reduces our cognitive load. So it makes our kind of execution way faster. So imagine if, say, when I'm coding, I still need to like spend a lot of time figuring out how to move my fingers to press each key on my computer keyboard. That might be kind of like I will be a pretty slow programmer. Maybe I wouldn't be able to kind of like do any real research at all because I spend most of my time just kind of typing on my keyboard. And secondly, I think another reason, which is actually related to kind of like my longer term vision of this research, is that by internalizing these basic skills, by making these basic skills as our second nature, we basically can focus on things that are more complex. So for example, a pianist, they are probably not focusing on whether they press each individual key correctly or not, but instead they are focusing on, let's say, the expression and the flow of the music, which is something that you can only spend your attention span on when you have like basically made the basic skills to be your second nature. So up to this slide, I've been talking about the reasoning systems in the human brain, but obviously I'm a researcher on natural language processing, so I work on language models. So why am I talking about the human brain reasoning systems? So the reason is because if you look at the reasoning in language models, we can find some interesting analogies. So for example, what is system 2 reasoning in a language model? It is actually commonly known as chain without reasoning, or I think the initial paper framed this as a sketchpad. So here I directly ask GPT-4 this grade school math question, and we will see that the response given by GPT-4 is exactly just like how kind of humans perform system 2 reasoning. So because this will be an example I use throughout my slide, I will actually read this example in its entirety, because this is a running example that we will kind of refer back kind of later in the experiment part of my talk. So this example is actually pretty simple. It says, assume his bookshelf has 120 books. She has 10 books on history, twice that many books on literature, and the rest are science books. How many science books does Asumi have? So if we prompt a large language model, GPT-4, with this question, this is the response that it returned. And if you look at this response at a high level, you will immediately see this structure of first reasoning about individual steps required to arrive at the final answer, and followed by the final answer itself. And I will not go into details because this is a really simple kind of grade school math problem. But the answer and the reasoning process given by GPT-4 is exactly correct. So I say language models today are pretty successful at doing system 2 reasoning. But what about system 1 reasoning? What if we change this prompt by simply adding this requirement to directly output the answer without producing the intermediate reasoning steps? What will happen? So interestingly, the model is able to follow the format of this request. But unfortunately, the answer given by the model, which is 80, so the correct answer, I think on the previous slide, should have been 90. But unfortunately, the answer is just kind of incorrect. So there actually are like even more obvious examples of such system 1 reasoning failures. So here is an example proposed by or discovered by my PhD co-advisor, Professor Schieber. So the answer is, which is closer to Ogden, Utah, the Empire State Building or the moon? Directly give the answer, do not think step by step. And if you ask GPT-4 this question, it will directly say the moon, which is obviously wrong. And by the way, to make sure that all the examples used on my in my slide on my talk are reproducible, I actually added the links to these shared GPT conversations at the bottom of my slides. So one question you might ask is, especially if we revisit that reasoning example of like a kind of answering grade school math question, is that why would we expect a language model to be able to do that? After all, maybe like as human beings, we cannot solve such problems without writing down the intermediate reasoning steps. And here's the reason why I believe it should have been possible for language models to perform system 1 reasoning, at least for the examples that I have shown so far. The reason is because language models, they have a different architecture as our human brain. If you think about what is happening before producing each output token, there are actually multiple layers of feed-forward network. And one kind of intuitive idea is, why couldn't the model just use each layer to perform one step of intermediate reasoning? For example, why can't the model use the second layer to do the first reasoning step? Why can't it then use the third layer to build on top of that to perform the second step of reasoning, and the fourth layer to the third step of reasoning, such that at the output side, it will get the correct answer? And actually here in this example, I'm showing a transformer model with 4 layers. But actually, if you look at how many layers our language models have today, they are actually like way beyond that. For example, before OpenAI kind of like closed source everything, if you look at the model architecture of GPT-3, it already had 96 layers, and they have each layer have a hidden size of 12,000. So you can imagine, at least for some kind of simple reasoning problems, such as grade school math problems, which probably requires 3 to 4, mostly 3 to 4 steps of reasoning, why can't it just use these 96 layers to figure out the answer directly without having to explicitly produce the intermediate reasoning steps? And this is the kind of intuition of why we believe it should have been possible for language models to perform system one reasoning. But then one might ask, but why can't these models do that yet? Like, what's the reason for their failures on such tasks? Given that here I'm kind of proposing this one potential way for the models to be able to achieve system one reasoning internally. So one reason that our hypothesis of the challenge might be because of the training procedure. So during training, if we train the model without this intermediate step supervision, or without the channel sort supervision, then the problem might be the model is unable to figure out the process itself. So by analogy, imagine if we want to teach a kid how to do, say, multi-digit multiplication by showing the kid multiple examples of input to output. And then we give this kid kind of a new input equation, and then we ask this kid to produce the output. Maybe it is really, really hard for the kid to figure out what's the output because they were not shown the process of arriving at or the process of mapping the inputs to the output. So without the channel supervision, maybe they cannot learn this process. That's the reason why we see these kind of system-wide reasoning failures in existing models. So if we think about the kind of the system one reasoning, the system two reasoning kind of paradigms, so now we are like by analogy, we are saying that system two reasoning in human brain is really similar to channel sort reasoning, and system one reasoning in the human brain is very similar to no channel sort reasoning. But actually, one kind of observation in our work is that there's actually a middle ground. So let's look at this kind of more carefully. So we rename kind of channel sort reasoning as explicit channel sort reasoning to basically contrast it with the implicit channel sort reasoning, which will be the focus of our work. So in explicit channel sort reasoning, both during training and during inference, we are using the channel sort. So during training time, we are using the channel sort to teach the model the process of solving the questions. And during inference time, we allow the model to produce these channel sort tokens before producing the final answer. But in no channel sort reasoning, obviously during inference time, we do not allow the model to output the channel sort reasoning steps, and they are required to directly output the final answer. But during training time, we are also not providing it the intermediate process, the channel sort supervision. And as I argued in the previous slide, maybe the model is failing because it hadn't learned the process of solving the problem, not because it doesn't have the capacity to perform the inference without using these intermediate channel sort steps. So between explicit channel sort reasoning and no channel sort reasoning, a middle ground that we identified is called implicit channel sort reasoning, where the idea is during training time, we allow the model to use channel sort steps as supervision to allow the model to learn the process of turning the inputs into the output. But at the inference time, we no longer allow the model to produce these channel sort steps before producing the final answer. So this implicit channel sort paradigm is a change in the training procedure, but at inference time, it is exactly the same as no channel sort reasoning. And at inference time, it just looks the same as system one reasoning in the human brain. So now let's go to the only approach slide in my talk, or I say the only kind of like a central kind of approach slide on my talk. So if I'm not presenting this slide clearly, feel free to interrupt me, because like I said, this is like basically the only approach slide. So our approach of achieving implicit channel sort is basically inspired by this internalization process that we mentioned in our earlier slide. So the intuition is we first train a model to perform explicit channel sort reasoning. So for example, here we are showing this example of, we break down the example into an input part and the channel sort reasoning part, and also the output part. So imagine if we train a model to perform system 2 reasoning, which is we train the model to first produce the channel sort reasoning steps before producing the final answer, then we can easily train a model to do that. Like our models today are pretty successful at doing this type of channel sort reasoning. But here is the key insight. In order to internalize this reasoning process, we propose that, so now we take this model that we have trained earlier, and then we change the data. So we remove the first reasoning token from the channel sort, and we fine-tune that model such that instead of directly producing the channel sort sequence, we fine-tune the model to start from producing the second channel sort token and onwards before producing the final answer. And now the model is basically forced to internalize this first channel sort token in its hidden state somehow internally, such that it can directly start from producing the second reasoning token and onwards. And after this stage, you can probably guess that the next stage is we further remove one more channel sort token, and we keep fine-tuning this model such that it can also internalize the second channel sort token, in addition to the first channel sort token, which is already internalized in the previous stage. And then we keep removing these channel sort tokens, and we keep fine-tuning until eventually all the channel sort tokens have been internalized. And now the model is simply trained to output the answer directly, conditioned on the input. And now we have basically achieved our goal of internalizing this entire reasoning process into the model itself. Is that clear? Any questions so far?
Hi, Professor. Can I ask a question about the methodology? You said you removed the first token from the COT at first, and
Yes.
I want to ask why don't you move the last token from the COT? Because I assume that from a perplexity point of view, from a perplexity perspective, the last token might have less perplexity, more certainty. So is it easier to fine tune the model by decreasing the loss to make the loss smoother? Thank you very much.
That is an awesome question, and I want to kind of answer the question kind of by first kind of like talking about the intuition behind doing that, and secondly, we actually have like a kind of an application study of actually internalizing from the end. So first of all, intuitively, the reason why we are internalizing from the left-hand side of channel sort instead of from the end of the channel sort is that, for example, imagine if we want to internalize the last token in the channel sort sequence, which is the 3 here. Imagine if we want to internalize this token here, but this token, in order to produce this token, it actually depends on all the previous tokens. So the best thing the model could possibly do after we remove this token and fine-tune the model is to kind of use the hidden state on top of this equation sign here to internalize, to store the information related to 3. And similarly, if you keep removing the 6 or the second to last, hey, sorry, I think there's some internet issue on my end. Can you still hear me?
Yes, we can still hear.
Sorry, where did I get disconnected?
you stop at so if you remove the last token, the information will be all stored at the equation sign, equal sign.
Oh, yes. Okay, yeah. So if we remove the last token, then the information has to redistribute it at the equal sign here. And if we further remove the token before that, then this information has to be redistributed again, kind of only towards kind of later tokens, but not earlier tokens, because this has a linear dependency on the previous reasoning token sequence. So if we keep removing that, we are basically essentially compressing many reasoning steps into the hidden states on top of one kind of equal sign. And that's the intuition of why it is hard to compress it in this way. Whereas if we remove from the left-hand side, then for example, if we remove this token 8, then it can potentially kind of find a way to redistribute token at the entire input side, not just kind of like having to compress it at kind of a fixed position. So that's the intuition. And empirically, we also did an ablation study of actually removing from the right-hand side, and unfortunately, it didn't do as well as removing from the first token. But I do think it is an interesting question to ask, like, what is the correct order of removing the Chern-South sequence? Like maybe we need to build a dependency graph or something, and then we figure out the correct removal order based on that. But for now, it's just that I think intuitively, I feel like it's actually mainly driven by this empirical observation, and also the intuition is that removing from the end will force the kind of the information to be encoded kind of like only at a limited number of tokens. Does that answer your question?
Yes, thank you very much.
Yeah. So this is our approach. But like all, I say like the deep learning training, like usually we need like a little more than the kind of the central approach. So the approach itself, I say, is extremely simple in my opinion. But we found that in order to stabilize training, there are kind of something else that we need to do. And if we do not use these kind of techniques, then what will happen is we found that after a stage transition, so recall that what is stage transition is? Stage transition is like we go to the next stage, and then we remove one more Chern-South token, and then we fine-tune the model. So the problem we noticed is that after each stage transition, we immediately see a loss explosion, because when the model has already been doing really, really well at starting from producing, let's say, the first Chern-South token, now all of a sudden, after the stage transition, all of a sudden we remove that token and we force the model to start from producing the second Chern-South token. Then all of a sudden the logics are entirely wrong, because the logics are already kind of confidently producing or predicting the first Chern-South token. So this is kind of the first cause, which is like the sudden change in the loss function after a stage transition. And our solution to this problem is when we train this internalization process, instead of directly removing that set number of tokens, we actually randomly remove a small number of extra tokens with a very small probability. And the idea is just that we want to prep the model to see kind of the next stage, even before we officially transition into the next stage. And the second issue is that the optimizer that we are using, which is AdamW, it is basically maintaining these moving averages of gradient estimates, the gradient moments. And because after each stage transition, the loss function has changed. So the gradient statistics no longer make sense. So we have to basically also reset the optimizer during transitions. But with these two changes to the training, I say like this works really, really well in practice. And the main experiment that we are using in this paper is multi-digit multiplication. And one big reason is that, first of all, it is a really, really challenging task for language models. And secondly, I think most importantly, we can easily control the level of complexity by varying the number of digits that we consider in the multiplication examples. So it's a kind of very controlled setting. And in our experiments, we were mostly kind of doing experiments on 7-digit multiplications. And the model we are using, which is kind of worth mentioning, is actually a GPT-2 Small model. So according to today's standard, I think like this is an extremely small model. So today people are counting the parameters of models by kind of billions, right? But GPT-2 Small only has like 100 million parameters with 12 layers. And yet we will show that even this small model can do extremely well in terms of multi-digit multiplication, way beyond what I expected initially. So more experiment details. So for the internalization, every 1/8 of an epoch, we just remove one more chain of thought token. So this is a fixed removal schedule. Actually, my advisors just suggested that, oh, maybe we should use some more like smarter removal strategies based on like thresholding the loss. But actually, even this naive linear removal schedule worked really well in practice. So we didn't further explore, I say probably like a better removal schedules that might actually be more efficient in terms of compute. And also I mentioned that kind of a crucial trick is that even before a state transition happened, we need to remove a small number of actual tokens with a small probability. And here is basically the kind of the exact probability distribution of the number of actual tokens we remove. And by the way, in case this is not kind of very clear to you, so basically, I say like over 90% of the time, it is actually not removing any actual tokens. So over 98% of the time, this random variable O is actually 0. And only with about like 2% of the time, we remove more than one actual tokens. So, but we found that even this small kind of like a kind of random token removal helps a lot in stabilizing the training process. So now we look at results. So we evaluate our models on 2 dimensions. So first of all, obviously we need to look at the accuracy of computing multiplication. And by the way, here by accuracy, we are using exact match. So for example, let's say if a model produces some result, and if there's a single digit error in the result, we will count that as a 0. Only if the model kind of predicts every digit in the result correctly, we would count that as a 1. So that's one dimension we look at, which is accuracy or exact accuracy. The second dimension we evaluate our models on is the speed of inference. And when we measure the speed, we normalize the speed as a percentage of the speed compared to a no chain of thought token, a no chain of thought model, which doesn't produce these chain of thought tokens before producing the final answer. So first, we look at explicit chain of thought results. For explicit chain of thought, for 7-digit multiplication, it is actually able to get 100% accuracy, which might not be that surprising, given that multi-digit multiplication has a pretty fixed kind of algorithm, and it's not surprising that a model can learn such dependencies. And in terms of speed, it's roughly kind of 10 to 15% the speed relative to no chain of thought, mainly because it needs to output kind of this reasoning chain of the intermediate partial products and partial sums in this long multiplication algorithm. So now, next we look at no chain of thought. If we directly train a model to produce the final output from the input digits, then in terms of speed, obviously relative to itself, you'll get 100 speed. But if you look at the accuracy, it's not that a bar is missing here. It's just that the accuracy of this approach is 0%. So for 7-digit multiplication, it is actually extremely challenging. Because 7-digit multiplication is like we have like 2 input numbers, each with like 7 digits long, and the result is like 14 digits, and it's extremely hard to train a language model to directly predict the output correctly. But what's encouraging is if you look at the results of implicit chain of thought, it can get 100% accuracy and 100% speed. And by the way, in terms of speed, it is exactly the same as no chain of thought. This is like not surprising because by construction, at inference time, an implicit COT model is the same as a no COT model because we just kind of internalize all the intermediate reasoning steps, and it is just directly producing the output condition on the input. So at inference time, it works exactly the same as a no COT model, which is the reason why it got the same speed. And the only difference is actually happening at training time. And in our paper, we kind of mostly conducted experiments on kind of smaller number of digits. And I'd be kind of like transparent that the real reason is that when we started experimenting with that, we didn't expect this method to work so well. After all, we were only using a GPT-2 Small model with 12 layers. So I was thinking something like, oh, maybe with 12 layers, it can only approximate like roughly 12 intermediate. It can roughly internalize roughly 12 kind of a constant multiplied by 12 number of intermediate reasoning steps. But actually, we found that we can scale this model to even like way more beyond that. So here we show our kind of approach scaled up into 20-digit multiplication. And we also built a kind of a demo on Hugging Face spaces. So if you are interested, feel free to kind of use the link at the bottom of the slide to try out this demo yourself. But it's, like I said, it's kind of just kind of working surprisingly well that it can predict the result of 20-digit multiplication correctly, which is a really, really challenging task. And to just kind of show people like how challenging the task is, if you look at the frontier reasoning models, they cannot solve it yet. So here I'm showing kind of the heat maps of basically OpenAI's reasoning models in solving multi-digit multiplication. So on the left-hand side of this figure, I'm showing the performance of O3 mini, and on the right-hand side, I'm showing the performance of O1 mini. Oh, and by the way, I wanted to clarify that the performance of O1 is actually roughly similar to O1 mini. I presume maybe like they are not kind of that. Maybe it's because multiplication doesn't require that much kind of common sense knowledge. It's just kind of more like kind of an algorithm thing. But anyway, looking at both models, and maybe I also want to kind of explain what the x-axis and the y-axis are. So basically, x-axis and y-axis are the number of digits in each number that we want to multiply together. So that's the reason why we have this 1 to 20 on each axis. And if you look at this, like basically for both models, I think they are unable to solve 20-digit multiplication. If you look at kind of the bottom, the lower right corner of each heat map. But if you look at our approach, even this small GPT-2 model, it is able to solve up to 20-digit multiplication really successfully. So for example, I want to clarify that there's actually like a small mismatch in the color bar shown here. So here, different from the previous slide, here the bottom of the color bar, which is like the kind of color corresponding to red, is actually 99.5%. Whereas in the previous slide, when we plotted the performance of OpenAI models, is actually 0%. So for our model, even for 20-digit multiplication, the performance is 99.5% accuracy. And if you measure the speed up compared to a no-train result model, for example, at 20-digit multiplication, it is 26 times faster. And it's not surprising because, say, for n by n multiplication, if you think about the number of intermediate reasoning steps, it's actually roughly on the order of n squared. So because our model doesn't need to predict this long intermediate reasoning chain, it is way faster in generating only output. And if you use our demo, you will kind of like probably have a more kind of intuitive sense of like how much faster it is compared to having to kind of produce this long reasoning chain first. So one interesting thing you might wonder is, if you look at this heat map, like it's not getting 100% accuracy. Interestingly, it's getting 99.5% accuracy. And you might wonder, where do we lose that 0.5% accuracy? What kind of problems it cannot solve? So this is actually a finding by my colleague, who was also a postdoc of my postdoc advisor, Professor Choi, when we were both at AI2. So he actually found that the failure cases mostly involve repeated digits. So you can actually try out our demo, and you can actually like try to have such examples yourself. So if you say you type a lot of repeated digits, then the result tends to be wrong. And to be honest, I don't know why. I think this is kind of an interesting question to answer going forward once we have a better understanding of the inner workings of these models. Yeah, so that is our main experiment, and actually I'm kind of pretty excited about the performance on kind of multi-digit multiplication, because like I said, it's a pretty controlled setting. But actually this method itself is actually pretty general. We can apply this to any problem with this structure of like input and then producing producing chain result before producing output. So we also conduct experiments on a bunch of other data sets. So one example is grade school math problems, as we saw earlier in my earlier slide. So we conduct experiments on the well-known GSM-8K dataset, and if you look at these different color bars, so so basically like each group here is one model that we tested this internalization approach on, and each color corresponds to one approach. So these blue color bars are explicit chain result performance, and these orange bars are no chain result performance. These green bars are implicit chain result performance. And I say, not surprisingly, implicit chain result performance, basically, if you look at accuracy, they usually lie in between no chain result and explicit chain result. And I say, like, there's no free lunch. Like, I think it's not surprising that it is getting a higher accuracy than no chain result reasoning, because during training time, we are using this additional supervision of chain result data. But it's also like doing kind of pretty well, even compared to say state-of-art models back then, GPT-4. For example, GPT-4, if we force it to directly output the answer without the final, without the intermediate reasoning steps, it's only able to get a bit beyond 40% accuracy. But we can actually use our approach to internalize the model to achieve about 50% accuracy on this task. So one really interesting thing that I was very concerned about when I was running these experiments is that I wonder if the model actually learned how to do reasoning, or is just overfitting to the training data set. So in order to test that, let's look at our running example, this bookshelf example, where this person has 120 books and 10 books on history, twice that many books on literature, and how many books are left. So first of all, obviously, this our model is able to get this kind of answer correctly. But then what I'm doing, what I will show is we can change these numbers to see if the output is changing accordingly. So for example, what if we change this 10 into 20? So when we change the number 10 to 20, we can see that, oh, the output actually changes kind of correctly, correspondingly. And what if we change this twice that many books into 3 times that many books? And again, it's actually able to kind of also react kind of correctly on the output side. So I say I'm kind of fairly confident that the model has at least learned kind of how to perform the calculations based on what's actually specified in the input problem. But still, it's actually pretty brittle. So one easy way of making the model fail is, say, if we change this science into history, how many history books does Asumi have? Actually, this is a trick question, because how many history books does Asumi have? We already give the answer basically in the second sentence. She has 10 books on history, but still the model is, I think, it's trying to do some calculation internally, but it doesn't make any sense here for this failure case example. And we have actually more examples on logic puzzle solving. So for those of you who are not familiar with logic puzzles, so in logic puzzles, the input is basically like it's almost like a logic puzzle is usually paired with a table, and the goal is to figure out, like, for example, there are 4 houses. Each house is occupied by a person. Each person has a name, and each person has a child. And then we were given a bunch of clues about kind of the people, the houses, and the children. And then we try to basically like rule out the kind of impossible possibilities. And finally, we need to figure out the mapping, like from the house to the kind of the person residing in the house to the child of that person. So essentially, like when a human being wants to solve that problem, usually, at least for me, I need to look at kind of I need to draw a table and kind of use that table to kind of guide me in solving the logic puzzle. But here, we are using it as an evaluation method or evaluation benchmark for our method. Oh, and by the way, just to clarify, this data set actually comes from my other colleague at AI2, Nuha, from her paper called Face and Fate, Limits of Transformers on Compositionality. So here, basically, these examples can be converted into the same input, reasoning, and output format as what we showed in our approach slide. So the chain of thought is basically like, using this clue, we can get this conclusion, and using that clue, we can get that conclusion. And finally, the output of the model is supposed to be kind of the which person is residing in which house, which child is which person's child. And here on this data set, interestingly, we found that both no chain of thought and implicit chain of thought actually outperform the performance of explicit chain of thought. This might appear surprising on its surface, but actually when we inspected the results, we found that the reason why explicit chain of thought has a lower accuracy on this task is usually due to compounding errors. It's because the chain of thought in this data set is usually really, really long, because like each clue is pretty long, and also the reasoning process can be long. And when there's like a single error in the reasoning chain, it can sometimes lead to kind of more and more errors, and eventually an incorrect output for explicit chain of thought reasoning. Whereas it seems that for no chain of thought, and implicit chain of thought, they are directly outputting the final output without having to output this intermediate chain of thought, which might be the reason why they have better accuracy. But again, on this task, we can again see that implicit chain of thought is getting better accuracy than no chain of thought. And again, I want to emphasize that there's no free lunch. It's because we are using additional supervision during training. So that basically concludes kind of most of our work on implicit chain of thought reasoning. But since then, there have been some follow-up studies, which I say either make us have a better understanding of what's happening inside the model, or there's actually, I think, a better model architectures to basically make the model kind of more powerful to potentially solve even kind of more challenging problems. So first, we look at this interesting question of how does the model achieve this? Like, how can a 12-layer GPT-2 model be able to solve a 20-digit multiplication problem, which might involve, let's say, 20 squared, which is on the order of 400 intermediate reasoning steps? And in this work, which is mainly led by Xiaoyan Bai at University of Chicago, and also Andrew Lee, who is also from Harvard University. He's a postdoc of Markins. So in this work, we answer this question by basically doing a bunch of probing analysis, and due to time limit, I wouldn't be able to get all details. But basically, the findings are it's mostly through attention that the model figured out a way to solve these multi-digit multiplication problems. So basically, attention builds a graph to kind of cache and retrieve partial products, and also this attention implements partial sums, and the digits are encoded via a Fourier basis. And because this reasoning process mainly involves partial products and partial sums, now the model is just replicating this process internally in order to output a final answer. For more details, I recommend looking at this paper, which is called Why Can't Transformers Learn Multiplication? Reverse Engineering Reviews Long-Range Dependency Pitfalls. Another really interesting work is, like I mentioned earlier, that kind of strengthens kind of the expressiveness of our model. So in this work called Coconut, which is from UCSD and also Meta, their insight was in the original implicit chain of thought formulation, we are directly training the model to output the final answer without any kind of horizontal kind of steps. It's just directly kind of outputting the final answer upon reading this entire input. And their intuition is, oh, maybe we should give the model some scratch pad to allow them to use before producing the final answer. But the scratch pad is limited. So for example, in their paper, they mostly use 5 steps 5 intermediate steps, and these steps are not in explicit COT tokens, but instead, these steps are in continuous vectors produced by the model itself. So instead of directly producing the final output given the input, they produce some kind of continuous vectors, and then they feed back the continuous vector to the next step, and then they do this a bunch of times, mostly 5 in their experiments, before kind of producing the final answer. And this turned out to be really successful. Oh, and if you look at the training process, I think it's a really kind of clever way of doing this. So in our approach, we were removing the channel style tokens and fine tuning, right? But in their approach, instead of removing, they replaced channel style tokens with these continuous steps. For example, every 2 steps or every 3 steps, they remove. They replace that with one continuous reasoning step. And they also staged their training into these different stages, like what we did. But their final model has this kind of more kind of reasoning on the horizontal side, and it was also shown to be successful on the reading data sets that they tested in their paper. Yeah, so in conclusion, I hope that it has become clear up to this point that a key kind of observation made in our work is that channel style tokens actually serve 2 different purposes. During training time, these channel style tokens, they provide supervision to show the model what is the process of solving the problem. At inference time, these channel style tokens, they act as a scratchpad to help the model to use this scratchpad to solve the task. And to us, these 2 roles can actually be separated, and the second role of the scratchpad can actually be replaced by the continuous hidden states inside the model itself. So during training time, we still use the channel style as supervision, but at inference time, we ask the model to just figure out a way to use their internal continuous hidden states instead of explicitly producing these channel style reasoning steps. And this whole process of gradually internalizing system 2 reasoning into system 1 reasoning is just inspired by this internalization process that's happening in the human brain. And with that, I want to thank everyone for listening, and I'm happy to take questions.